Yes, good morning. Today we're going to start talking about Chapter 7. Chapter 7 is entitled Estimates and Sample Sizes. And in particular, Section 7.2, which we'll talk about today, we're going to be estimating a population proportion with some desired characteristic of interest. Alright, really this opens up the third part of our course. Remember, the first part of our course was descriptive statistics, where we use visual devices such as histograms, box plots, etc. to organize and interpret data. The second main part of the course was probability, and as that's now drawn to a close, now we go after the real meat of the course. The real target is inferential statistics. And the real key word here is inferential, and in the branch of inferential statistics, we will make inferences about populations, which typically are too big to study, at least element by element. Make inferences about populations based on sample data. And that's the real goal, the real target of the overall course. Alright, motivation. Let me ask a question here. What is the worldwide population proportion of left-handed people? I'll just be informal here and I'll call it lefties. All right? How do we answer a question like this? What is the worldwide population proportion of lefties for all people of all time? Well, of course, the correct answer is that we don't know. And we never will know, because populations are, by definition really, too large to study element by element, and containing billions of people in the worldwide population here in this example. Well, we don't know the answer to this question, and we never will know it exactly because populations are too big. Well, how do we handle a situation like this then? Consider this. We take a sample, hopefully a representative sample of the overall worldwide population, and from a small sample we could compute the sample proportion. Of left-handers, I'll call it lefties. Alright, so in this way we'll use a sample data. We'll use sample proportion to estimate the population proportion, which typically we will never know. Alright, it's easy enough to compute a proportion of a sample with any desired characteristic of interest. Let's do a numerical example. Let's suppose in a sample of, let's say, 30 people, let's say that yields 5 people are lefties. Alright, so the sample proportion of lefties, well, of course, that's just going to be my number of lefties divided by the total number in the sample, and that turns out to be a 0.167. Alright, so we might claim that this sample proportion is a good estimate of the population proportion of lefties, and history has shown that about 10% of the population, or proportion of 0.1, is the widely accepted value for population proportion of left-handers. Alright, so based on this sample data, we make an estimate of this population proportion. That's the whole idea of what we're going to do today. Alright, we got to get some notation down. Little p, lowercase p, will indicate a population proportion with some desired characteristic of interest. Put down with some characteristic that we want to study, be it left-handedness, characteristic, or any other characteristic. Little p hat, it's lowercase p with a little caret on top of it, I call that p hat, will be designated as our sample proportion with the same characteristic of interest. Again, in wide strokes, if we've got a huge population, let's say a population proportion with some desired characteristic, I'm going to label that little p, and our goal is to, from this population, take a sample and compute a sample proportion, which we will call p hat. And I claim that p hat is what we call a point estimate of p. Point meaning it's just one number, one point on our number line that may or may not be a good estimate of p. Yeah. In our previous example, p hat was 0.167, and again, little p, generally accepted value, is 10% of population being left-handed. Alright, so that's the idea here. You're using this to estimate this, okay? Alright, again, another motivation. Sometimes p hat is a good estimator, or a good estimate of p. Right? And sometimes it's not. Depends on the sample data. And the sample data that you draw is subject to chance, of course. Alright, so instead of creating p hat, let me write this, let me change this. Instead of using p hat, our sample proportion, as a point estimate, I'm going to suggest a better way. Compute what we call an interval estimate of little p, our population proportion. Alright, well, what I'm going to do is construct a range of values, an interval of numbers on our real number line, and I'm going to construct it in this fashion. I'm going to take my p hat and subtract a quantity called cap e, that's our margin of error. We'll get to that in a minute. I'll then create a high end of my interval estimate. I'll call it p hat plus e, again cap e for our margin of error. Of course, p hat is the center of this interval, and the idea here is I've created an interval estimate, kind of a numerical bucket, that hopefully will contain the actual value of the population proportion. Put a question mark here. So the idea again here is this interval estimate, kind of a numerical bucket, that hopefully will contain little p, our population proportion. All right, our interval estimate now all it is, remember, it's this range of values that will create. I'll have a high end and a low end for this interval estimate. Interval estimate is also known as a confidence interval. You may have heard this phrase or this term before. Confidence interval. As we'll see, we can generate these interval estimates or these confidence intervals based on certain what we call levels of confidence. Confidence intervals often are abbreviated CI, cap C, cap I. And what we're going at here is with a certain level of confidence we can create a confidence interval that hopefully, or I might say probably, will contain little p. Alright, so that's the idea. We're creating a bucket, a numerical bucket that hopefully traps p in between. Alright, so that's where we're headed here. You've got to get some more notation and definitions down. Our level of confidence. I sometimes abbreviate it as LOC. The book does not. Just be aware of that. It's defined as 1 minus alpha. Now don't panic. 1 minus alpha, we'll talk about alpha later in the course. And typical values for your level of confidence are 0.9, 0.95, or 0.99, kind of a low, medium, high for levels of confidence. Our margin of error, and we call that cap E, can be ground out according to a somewhat nasty formula. You can see it in the book. Cap E equals Z sub alpha over 2 times root P hat Q hat over N. Now don't panic, because the TI 83 and 84 will compute this value for E upstream with a new function operator we're going to talk about today. Alright, of course, P hat is our sample proportion with some desired characteristic of interest. Q hat is, as you might guess, the complement of P hat. Little n is, of course, our sample size. And, of course, our goal, our confidence interval, is going to look like this. It's going to be a range of values to estimate P. The lower bound is going to be P hat minus E. The upper bound is P hat plus E. Of course, P hat, our sample proportion, is smack dab in the middle. And again, is the real value of P contained in this interval? Hopefully, or probably, you might say, the answer is yes, or with a certain level of confidence. The answer is yes. All right, I want to jump in and do an example, a numerical example, and let me get a fresh screen here. We're going to be introducing a new operator on our calculator. I want to look at example 3 on page 331. Let me turn there myself. Example 3, page 331. All right, constructing a confidence interval, poll results. In the chapter problem, you may recall the chapter problem is at the beginning of each chapter, kind of a theme problem for the entire chapter. In the chapter problem, we noted that a Pew Research Center poll of 1,007 randomly selected U.S. adults showed that 85% of the respondents know what Twitter is. The sample results are n equals 1,007 and p hat equals 0.85. Remember, p hat is a sample proportion. Let me write that down. Our sample, kind of a large sample, was 1,007 people. And we asked these 1,007 people, do you recognize Twitter? And 85%, or a proportion of 0.85, said that they did. I want to focus on Part B of Example 3. Part B asks, find the 95% confidence interval estimate of the population proportion P. Let me write that down. Find the 95% confidence interval for P. And now, little p is the population proportion of people who know what Twitter is. Okay? And typically we will never know little p exactly. Populations contain millions, maybe billions of elements, and we can ask all the people in all the world, do you recognize Twitter? Alright, so what we're going to do is create a confidence interval to estimate that population proportion, right? Alright. What I'm going to do is introduce this new calculator command. We're going to use this command. It's one prop z int. Right? It's under the tests menu, under the stat button menu. Right? So this is the name of the operator that will give us our confidence interval, and it does it pretty easily. Use one prop z int, not z test, z int, right, on the TI 83 or 84. Alright, how do we get there? Well, get your calculator out, make sure your home screen is clear, and I'll press the stat button, and then you'll see a test menu under that stat button, and then you'll have to scroll and select this command, one prop z int. Alright, now the reason we use one prop z int, one prop because we're going to be estimating one population proportion, and the z int, well, the int is for interval, and the z value is because your margin of error is based on a z-score. Okay, you'll see the margin of error, which the calculator does for us, involves a z-score. Hence the command one prop z int. Okay? Alright, so call up this command in your home screen, and we should see the following. One prop z int, or z interval. It prompts you for an x value, an n value, a confidence level value, and there's a calculate command at the very bottom of that input screen. Now x is the raw count in your sample that has the desired characteristic of interest. Alright, for this particular problem, well, we don't have a raw count. We have a kind of a percentage or proportion count of this sample that recognizes Twitter. Alright, so the raw count here, it's going to be the round of, well, if you've got 85% of the population recognizing Twitter out of 1,007 people, I'll just take 0.85 and multiply it by 1,007, and I'm going to round to the nearest integer. The calculator input for this command has to be an integer, a raw count, right? Alright, so I grind that out, and I'll get, well, the round of that product is going to be 856. So that represents the 85%, or the 0.85 proportion of my sample that recognizes Twitter. Alright? Sometimes the raw count is given to you explicitly. Sometimes you have to do another little step like this to figure it out. So be aware of that. My sample size, pretty straightforward, is 1007. What's my confidence level here? How sure do I want to be to capture P in my final answer? Well, it's 95% or 0.95. Alright, so once I've entered in these three values, I can then scroll down and hit calculate, select and enter on that calculate command, and I get the following result. 0.828, comma 0.8721 in what they call open interval notation. Now this is my confidence interval. It's my 95% confidence interval for the population proportion of those who recognize, let me write it out here, those who recognize Twitter. All right. Notice the calculator also as part of your output will give you the p-hat value, which of course we already knew was 0.85, and little n, our sample size, with 1007. But again, this is what we're going after here, the confidence interval. All right, what we're saying here is this lower and upper bound creates, again, kind of a numerical bucket which hopefully, I might say with 95% probability, or with probability 0.95, actually will contain little p. I like to write the answers for confidence intervals in this fashion, in a double-sided inequality fashion. What I'm really saying is this. Oops. P is trapped within these boundaries within 95% confidence. Right? And let me write that down. This is my final answer. This is my 95% confidence interval for little p, the population proportion of people who recognize Twitter. Okay, what I'm really saying here is this. In some of the homework problems, the book asks you to conclude with a explanatory type statement. This tells me 95% of similarly constructed intervals will actually catch P or contain P. Alright, so when the book asks us for an explanatory statement, some interpretive statement, they're asking for something like this, okay? Let's see, I want to do a couple more. Let's look at number 14. In our textbook, this is on your homework list, this is on page 338, I believe. Let me turn there. I want to turn there also. Alright, it says, from a 3M privacy filters poll in which respondents were asked to identify their favorite seat when they fly, n equals 806, x equals 492. Now, they do give us a raw count here. So the sample size was 806. Right? X equals, again, this is a raw count, and it's given explicitly. We didn't have to calculate it like in the last example. 492 who chose the window seat. So they're saying 492 people out of the sample of 806 chose the window seat when they fly as their favorite. Level of confidence. LOC. Remember, LOC is designated as 1 minus alpha. We'll talk about alpha, maybe not so much today, but later on. 1 minus alpha is your level of confidence, and here it's explicitly given to us as 0.99. Alright, so we want to construct a 99% confidence interval for the number of people, or the population proportion, who identify their favorite seat as the window seat when they fly. Alright, so again, we're going to use our oneprop_zint command. Hit your stat button, go to the test submenu, and then the oneprop_zint command, and I'll enter in the following. Well, my raw count for this problem, it was given to me explicitly, is 492. So I just enter in 492 for this x value, and you're restricted to integer values, remember. The sample size was 806. The confidence level was given to us as 0.99. And I highlight calculate and enter, and I get the following result: 0.56618, comma 0.65467 in parentheses interval type notation. Alright, now remember, this is kind of an umbrella that we're hoping will contain P, the population proportion of people who indeed choose the window seat as their favorite seat. So 0.56618 is the lower bound for this interval. 0.65467 is the upper bound. Now remember, p hat is right smack dab in between. Cap E, we never really see cap E. The calculator computes it upstream for us, but I just want to give us a fundamental idea of what's going on here. Is little p within these bounds? I suppose you could say, well, maybe not, but we can say that with 99% confidence. Okay? So my final answer I would write like this in double-sided inequality notation. I'll say my 99% confidence interval for P, the proportion of people who like window seats the best, is going to be this interval. 0.56618 is less than P, which is in turn less than 0.65467. So when I ask for confidence intervals, I would like you to return a double-sided inequality of this type. Okay? Alright, so hang on a minute. Alright, so this is the confidence interval estimate we seek. Actually, this is the answer to part C in our textbook, and part D asks for an interpretive statement. And I'll write something like this: 99%. We can be 95% confident that this interval actually contains P. And remember, your answer depends on your sample data. So your answer might change depending upon the sample data that you collect. Okay, so remember that. Alright, number 23 I want to talk about as well. Number 23, this is on page 339. Alright, it talks about job interviews and body piercings and tattoos in the presence of job interviews. Let's read the problem. In a Harris poll of 514 human resource professionals, so right away I know I'm going to be surveying 514 human resource professionals, it says 45.9% said that body piercings and tattoos were big red flags in the interview process. So notice they don't give us a raw count, but they do give us a sample proportion. 45.9%, or I'll use a decimal 0.459 proportion. Alright, they're kind of babying us here a little bit with Part A. It says, among the 514 human resource professionals who were surveyed, how many of them said that body piercings and tattoos were big red flags, grooming red flags? Alright, well, they want the raw count of these 514 that said tattoos were a red flag. Alright, well, they don't give us a raw score, a raw count, they give us a proportion. So all I need to do is take that 0.459 proportion, multiply it by 514, and I'll get 236 rounded. Now you've got to round these values that the calculator gives us, because when I use the one prop zint, I'm only allowed integer values for that x input. So I'll say x here is going to be 236. B. Construct a 99% confidence interval. Estimate of the proportion of all human resource professionals believing that body piercings and tattoos are big grooming red flags. Alright, so let me cut right to it. I'm going to use my one prop zint command. Again, you get there through the stat button and the test submenu. For my raw count with that characteristic of interest, I'll say 236 of these human resource people said tattoos were red flags. My sample size was 514. My confidence level was 0.99. Let me check that in part B, 0.99. And I'll then highlight calculate for the following result. Hang on a minute. 0.40253, comma 0.51576. Alright, so I claim then my 99% confidence interval estimate for P, the population proportion of human resources directors that say tattoos are no-nos, is going to be, and I'll put it in double-sided inequality notation, okay, so there's my final answer for part B. Okay. Alright, now look at part C. It asks us to repeat this for 80% confidence level. Yeah, so in part C, they want us to construct another confidence interval with the same information, except to change the confidence level from 99% to 80%. I'm going to need some more room here. Alright, so this is part C. Again, I'll use my one prop zint for interval command, and the raw count of, let's see, people, human resources directors out of that 514 who say tattoos are red flags is 236. The sample size is 514. The C level, again, we're going to change the confidence level from 0.99 to 0.8. Alright, then of course, once I enter this, highlight and select calculate, and I get the following result, 0.43098 and 0.48731. Alright, so I claim my, well, not 80% confidence interval estimate for P, the population proportion of human resources directors who say tattoos are red flags, is the following. 0.43, make sure I get it right here, 0.43098 is less than little p, which is in turn less than 0.48731. Alright, part D in this problem asks us compare the confidence intervals from parts B and C. And I did them both up here above for you. Compare the results from part B and C. And identify the interval that is wider and why is it wider. So I'm going to leave that for you to do. Which is wider? B or C, and more importantly, why? Right? And we will be investigating this question both in in-class tests and online exams. So be aware of that. And that's the last example I wanted to talk about today in this section. So this concludes the 7.2 online class, Estimating a Population Proportion.